Okay, the first speaker of this morning is Dan Cristofaro-Gardiner. He's moving from Harvard to Santa Cruz. And he's going to talk about two or infinitely many closed orbits.
Okay. Thank you very much for the introduction. It's really fantastic to be here. I really love it here. So I want to tell you about some joint work on dynamics of Rabe vector fields. It's joint with Mike Hutchings and Dan Pomerlano. So I'll get to it. This whole talk is going to be about three-dimensional dynamics. So I'm going to be working on a closed three-manifold. We've seen the definition of a contact form before, but just to remind you, in order to talk about Rabe vector fields, I need to talk about contact forms on this three-manifold. So we have lambda is contact, which means that if I take lambda and I wedge it with d of lambda, then that's non-zero. And that means I can define the Rabe vector field it's defined by the equations. Well, the Rabe vector field, it's in the kernel of d lambda, and it's normalized to have lambda length 1. Okay. Now, there's a theorem. As I said, I want to talk about the dynamics of vector fields like this. There's a theorem about this kind of thing due to Taubes, which says that that this vector field R, again, everything in this talk will be on closed three-manifolds. So I'm always just assuming I'm working on a closed three-manifold. So Taubes showed that this vector field R always has at least one orbit, one closed orbit. This is called a Rabe orbit. This is the three-dimensional case of the so-called Weinstein conjecture. So this is the three-dimensional case, three-dimensional Weinstein conjecture. And the basic question behind our work is what more one can say about the number of closed orbits that this Rabe vector field must have. Okay. By the way, are there any questions? And please stop me if you can't read anything. I took a survey of a couple people about whether they preferred PowerPoint or Chalk Talk, and Chalk seemed to be the consensus, but it's kind of hard to see because it's a big room. I mean, we have this wonderful thing here, but in order to use this wonderful thing, right, I have to point at the right thing. So if you want me to point at something so that our wonderful camera person can put it up. With the writing within the frames. It's too wide for the camera. Okay, so more. Okay, within the lines, yeah. It's like elementary school again. Okay, so I'll try to be a little less wide. But while I'm at it, should I point to anything? Okay. Anyways, so this is the basic kind of question here. How many closed orbits must the Rabe vector field have? So the first theorem in this direction is due to Michael and I. So this is my joint work with Michael, which says that R must have at least two closed orbits. Always has at least two closed orbits. Okay. That's not what I'm going to talk about today. The question that I want to talk about today is what more one can say. So examples exist with exactly 2. But what happens? So the question is, what happens when there are more than 2? Happens when there are more than 2 orbits. Okay? And so the theorem that I want to tell you about is as follows. Okay, so I'm going to try again to keep the margins a little bit smaller. So let's see. So the theorem, as I said, this is joint work with Michael and Dan Pomerlano. So we want to make some assumptions. I'll state them, and then I'll briefly review what they say. So I want to assume that lambda is a non-degenerate contact form on Y. Okay. I also want to assume that the first Chern class of the contact structure associated to lambda is torsion. Okay. Then the conclusion of the theorem, so then lambda has either 2 or infinitely many distinct closed orbits. Okay. So that's the theorem that I want to tell you about. Let me briefly spell out this notation here. So this psi here, this is just the contact structure associated to lambda. Okay, actually, I'm just going to write it like this. And, well, what does it mean for a contact form to be non-degenerate? We already saw this in an earlier talk. I won't write it on the board. Later, actually, I have to say a little bit more about this. But anyways, we have this linearized return map. And I'm just saying that 1 is never an eigenvalue of the linearized return map for any orbit, including the multiple covers. Okay. So here's the statement of the theorem. Are there any questions about this? People can see it. I'm not so good with the margins. What do I mean by torsion? Okay. Thanks. Sure. I mean, so this I'm looking at the kernel of lambda. This is a two-plane field, so I want to think of it as a complex vector bundle. I'm taking its first Chern class. So this lives in H2 of the manifold. And I just want this to be a torsion class in H2. Okay. Does it make sense? So any more questions about the statement of the theorem? What?
How do you decide by calculation if it is torsion or not?
You compute its Chern class, but I mean I don't know if I have a great answer for that. I mean it's usually not so hard to tell. But for example, I'll make a remark. So I was going to make a remark. The simplest case where this is torsion is where H2 of the manifold is only torsion. Then the Chern class. So for example, already there are many interesting Rabe vector fields on rational homology spheres, and then this condition is automatically satisfied. Yeah, I don't know if I have anything more intelligent to say. I do want to make some remark along those lines. Okay. So the case with exactly 2 orbits was previously studied by Hutchings and Taubes. So the case with exactly 2 previously studied so what Hutchings and Taubes proved, they prove here that my manifold Y must be a lens space and both orbits are elliptic. So combined, so this is due to Hutchings and Taubes. And combining this with our theorem, it's easy to construct examples where every non-degenerate contact form has infinitely many orbits. So, for example, you can take a rational homology sphere that is not a lens space, and then any non-degenerate contact form has to have infinitely many orbits. Okay. Anyways, so that's the introduction. I want to tell you some things about the proof. But yeah, please ask. The remark. No, this is just, yeah, so this is just assuming non-degenerate, so I'll write that. Yeah, so the non-degenerate case, let me say it like this, the non-degenerate case with exactly 2 orbits was previously studied, but you don't need C1 to be torsion in Hutchings and Taubes' theorem. Yeah. Thanks for asking. No. In my paper with Hutchings, there's no assumptions whatsoever. Yeah. Great. I like the questions. Make me feel like you can read it. So any more questions? Okay. Well, just stop me if you have more questions, and I'll point at it again. The most important thing is that you understand the statement of the theorem. By the way, another interesting question is to what degree these assumptions are necessary. I don't know. I suspect that one can remove all these assumptions completely, and this is sort of something I'm quite interested in. But if I knew how to do it, I maybe would have already done it. So. But there are some ideas that I can tell you about if we have time. Okay. Anyways, let's talk about the proof some. It's a pretty complicated proof, so we definitely won't be able to get through it. However, I want to give you some ideas of the proof. Well, actually, I'm going to start with a sketch of the proof. Okay. So how does the proof work? Well, we want to assume the following. So basically, for the entire argument, we want to assume, in addition, that there are only finitely many orbits. So sometimes I write finitely many orbits. By this, I mean embedded orbits. Obviously, once you have one orbit, you have all their multiple covers. Okay. So, of course, we can always assume this. Otherwise, the theorem is certainly true. So what we'll show that combined with the other assumptions of the theorem, combined with the other assumptions, of the theorem, the flow always admits a global surface of section. So I'll tell you what that is. I don't think anybody's introduced a global surface of section. First, I'll draw a picture for you. Okay, so here's the kind of picture that you should have in mind. So now I'll maybe explain this picture. But here is a picture of a global surface of section. So again, we want to assume, in addition, that there are finitely many orbits. And this is an important assumption because there are many cases of Rabe flows on non-degenerate Rabe flows on manifolds with torsion contact structure, which definitely don't admit global surfaces of section. So this is a very key assumption here. Okay, so what is this global surface of section? So namely, what do we want? We're looking for a surface. So the idea behind this global surface of section is that I want to reduce questions about counting periodic orbits for the Rabe vector field to questions about counting periodic points for some surface diffeomorphism. That's the idea here. So I want some surface sigma. I want it to be in Y. I'll write it like this. So I want sigma, a surface. I want it to be embedded away from the boundary. The boundary could be multiply covered. Okay, so I have some embedded surface. I want sigma, I want the interior of sigma to be transverse to my Rabe vector field. Okay. And I want every flow line, the key point is I want every flow line of R away from the boundary of sigma to hit sigma both forwards and backwards in time. Sigma both forwards and backwards in time. So I'll go back to my picture. Right, this is why it's a global surface of section. The key is that, so I have the boundary of sigma, which is supposed to lie at closed orbits of the Rabe vector field. And then away from the boundary, I want to be able to define a well-defined Poincare return map. So I want to be able to launch off from the surface and then return at some time, and I get a well-defined map that way. Okay? I should actually write on the board that the boundary of this has to be at Rabe orbits, but so I want the boundary of sigma at Rabe orbits. Okay, so the key point of all that is what I was saying before. Once I have a global surface of section, that will imply that the periodic orbits, so that will imply I can define this Poincare return map, P, going from the interior of sigma to itself. And the periodic, the Rabe orbits, so the simple Rabe orbits will be the same thing as, well, I have the boundary of sigma, which is some collection of Rabe orbits, and then I have periodic points of this map P. Simple periodic points. Okay? So in other words, as I was saying, if I have a global surface of section like this, I can turn this question about counting the number of Rabe orbits into a question about counting the number of periodic points of this surface. Are there any questions about what I've said so far with the global surface of section? Do you want me to point to anything? Okay, great. Okay, okay, who cares? Well, the nice thing is that there's a great theorem about, surface diffeomorphisms that's quite similar to this tour infinity business. So then I can apply the following lovely theorem of Frank's. So this is a famous theorem of Frank's. There are various ways to state it. One way that works for us is if I have if I have any area-preserving homeomorphism of the open annulus with at least one periodic point has infinitely many. Okay. So I think Marta stated a fairly similar theorem in her talk about surface diffeomorphisms. I will note that this is actually a theorem about surface homeomorphisms, which I don't know if it's essential to the proof, but it makes it easier because you don't have to worry about certain things. But so now you can sort of imagine how the proof would go. So Frank's is saying if you have an area-preserving homeomorphism of the open annulus, then if you have at least one periodic point, you have to have infinitely many. So remember, we want to prove tour infinity. So let's imagine that this was our global surface of section. Well, this is a disk. So by sort of classical work, this return map has to have a fixed point. And then I can remove the fixed point, and then I get a map of the annulus. So that could have no periodic points, in which case I would have two, or it could have at least one, in which case, by Frank's theorem, it would have infinitely many. Okay? Now, our surfaces of section, they might not be disks. I mean, they could be cylinders, in which case you can apply Frank's theorem directly. In fact, they could be genus zero curves with 3 boundary components in our proof. In that case, you have to collapse one of the boundary components. But this is just for area-preserving homeomorphisms, so it works as well. But it is very key. The thing that's very important is that we need genus 0 global surfaces of section. So we're going to get some global surface of section, and it has to be genus 0 to apply Frank's theorem. Okay. So are there any questions about that? Yeah, yeah. So then you would have infinitely many. Yeah. So in principle, you could, from our proof, you could have a genus 0 global surface of section with 3 boundary components, and then the Rabe flow would in fact have infinitely many. But the way we're saying that is, in that case, you would collapse one of the boundary components. Exactly. Yeah, exactly. That's right. Yeah. Okay. So, well, okay. So we need this surface of section. In fact, we need it.
So to apply Frank's theorem, you need a section with genus 0.
Genus 0, exactly. Yeah, I'm going to write that. And so actually, so this is actually all very standard, I mean, by this point. The first kind of ideas of this form, at least that I know of, were used by Hofer, Wysocki, and Zender, who proved a similar theorem about convex subsets of R4. The main innovation in our proof is how to actually find this global surface of section. So we want a G equals 0 global surface of section. Well, so how can we find this? How to find? Okay. Well, there's a lovely idea, still due to Hofer and his collaborators. So we'll want to find this by the projection of a holomorphic curve in R cross Y. So we'll find it as the projection of a J holomorphic curve in R cross Y. Okay. So again, that idea goes all the way back to Hofer and his collaborators. The main innovation in our proof is how are we actually going to find this global surface of section? So we'll find this curve using embedded contact homology. Okay. And I'll tell you what embedded contact homology is and what it has to do with this. And presumably maybe someone here hasn't seen what a J holomorphic curve is before, so I'll tell you that too. But these J holomorphic curves, anyways, they live in symplectic manifolds. This is a contact manifold, but this thing is a symplectic manifold, but it obviously admits a projection map down to Y. So to find a global surface of section like this, we want to find some kind of nice J holomorphic curve in R cross Y. I'll tell you what that curve should look like, and then the point is that'll project to a global surface of section. Then we can run Frank's theorem. We do want a genus 0 curve here. And we'll find it using this variant of contact homology. So that's the sketch. I'll get into some details. But are there any questions about the sketch? I mean, the details get a little involved, and you won't be able to see all of them anyways. So this is kind of very good to understand the sketch.
Can you say at this point where the torsion hypothesis comes into
I can say it, yeah. So it comes in this step. What happens, I mean, you'll see it a little bit more when I get to some details of the proof. What happens is that embedded contact homology always gives you many holomorphic curves, but they need not have genus 0. And that's a problem in various parts of the proof. So what happens is that, in general, if you run this argument and you don't have some kind of torsion hypothesis, you don't have good ways of controlling the genus, at least with the machinery that we currently have. I mean, I actually believe that this hypothesis is unnecessary. But with the tools that we have, we don't have good control over the genus of the curves that appear unless we assume this torsion business. Hopefully, when I get to the details, you can see better where the torsion is coming in. Yeah. But it's a pretty technical thing that just lives on this embedded contact homology side. So anyways, just to emphasize, if you haven't seen these arguments before, basically everything here is standard for these kind of problems, except for this strategy of finding the curve with embedded contact homology. As far as I know, no one's done something like this before. And there's only like 5 people who work with embedded contact homology anyways. So I probably know. OK. Yeah. All right. So any more questions? OK. So let's talk about some details. So, there are a lot of details, so I'm going to go through things, not exactly quickly, but in not much detail. Okay. So the first point is, what is this embedded contact homology? From our point of view, we want to use embedded contact homology to find holomorphic curves. But we should try to understand what this thing actually is. Okay. So this embedded contact homology, I'm going to write it ECH of, well, it eats your contact form, and it eats a class, gamma, in H1. So we're going to fix a class, gamma, in H1 of the manifold. Okay. So this embedded contact homology is the homology of a chain complex ECC. Okay, so what should this chain complex look like? Well, I want to study Rabe orbits, and I want to find some holomorphic curves. So I should combine these in some way. And that's what this chain complex looks like. So this chain complex, ECC, of y lambda gamma, is freely generated over Z2 by orbit sets okay. Alpha equaling, so finite orbit sets like this, where what I want is I want these alpha i's to be distinct embedded orbits and I want these mi's to be positive integers. I also want mi, well, there's a slightly mysterious condition that I'm about to state, but let me briefly touch on these other 2 conditions which are less mysterious to ground you in reality. So again, I want to study closed orbits of the Rabe vector field. I want to study these Rabe orbits. So the first observation is if I have a Rabe orbit, I can go around it a bunch of times and I still get a Rabe orbit. That's what these positive integers are supposed to be keeping track of. The way I want to write a generator of embedded contact homology is just some finite collection of Rabe orbits, And essentially, I look at the underlying embedded Rabe orbit, and I look at the covering multiplicity. And these things have to be distinct. So I should never see, I don't get like if you were to write this as a monomial, you don't get something like alpha squared times alpha cubed. You just take, you're only allowed alpha once. You get, like an alpha to the fifth in that sense. So you just collect the total multiplicity. So that actually looks relatively standard, similar to what you would see in variants of symplectic field theory. The next condition is a little bit strange. So this integer, I want it to be 1 if my orbit alpha I is hyperbolic. Okay. So actually, you might not know what hyperbolic means. So I will tell you. But you might know what hyperbolic means. And even if you do know what hyperbolic means, this looks a little bit strange. And interestingly, it actually plays an important role in the proof, although I don't think we'll get to that level of detail. But anyways, this is saying, remember this covering this number, this is like a covering multiplicity. So this is saying in my chain complex, I don't allow any multiply covered hyperbolic orbits at all. So if you're familiar with symplectic field theory, you might have seen these like bad orbits. You throw out bad orbits, which are like even multiple covers of certain hyperbolic ones. But here, almost everything is bad when hyperbolic orbits are in play. So I throw out all the multiple covers of hyperbolic orbits for somewhat mysterious reasons. Anyways, that's my chain complex. I don't want to write on the board, but I'll just say in words what I mean by hyperbolic. Remember, non-degenerate means that I always have this return map, and I know that 1 is never an eigenvalue. So it turns out that the eigenvalues have to multiply to 1 because it's a symplectic map. Hyperbolic is the case where they're both real. The other case is where they both lie on the complex unit circle, which is the so-called elliptic case. Okay? So anyways, that's my chain complex. You can also define it over Z, actually, but we don't need that. For what we want, we just want to define it over Z2. So are there any questions about the chain complex? Okay, so I have to tell you what the differential is. That's sort of the hard part. So the differential D, well, it counts ECH index 1 J-holomorphic curves from alpha to beta. In R cross Y, so from alpha to beta. Okay. So I'm going to draw a picture. So I have some J-holomorphic curve. I promised you at least a brief explanation of what a J-holomorphic curve actually is. So I'll say that in words. But anyways, these J-holomorphic curves, they live in R cross Y. And, well, a differential coefficient is going to correspond to a picture like this, where I have an orbit set alpha at plus infinity, and I have some other orbit set beta at minus infinity. And the point is that if I look at the differential coefficient d alpha, and I look at that along beta, so namely, this is a count of points in the space of J-holomorphic curves between alpha and beta, as above. And it's the space of I equals 1 curves. And there's actually an R translation here because I have an R action. So I want to mod out by that. Okay? So let me, at least from the non-experts, say a tiny bit about what these J-holomorphic curves are. So J-holomorphic curves, of course, are used all the time to study symplectic manifolds. Here, my symplectic manifold, well, I'm given a contact manifold, but if I take its product with R, I get a symplectic manifold. We saw that in a previous talk. Anyway, so this curve here, it's like a you should think of it as like a complex curve. So if I were studying a complex manifold, I could look at complex curves in that manifold. If I have a symplectic manifold, it might not be complex, but it's still even dimensional. And Gromov realized that it's productive to study analogs of complex curves to find with an almost complex structure on this thing. So it's kind of a long story. But certainly J-holomorphic curves have been used productively in symplectic geometry. And here I'm doing it to this symplectization that actually has already been discussed in previous talks. So at any rate, I will emphasize that the domain of my curve is supposed to be punctured. So it's worth emphasizing that the domain of our curves is a punctured Riemann surface. Punctured Riemann surface. Riemann surface. And our map U is, so the map is asymptotic to Rabe orbits at the punctures. Okay. So I'll see if you have any questions about that. But anyways, this is also standard. The non-standard part is this ECH index, and we want to say what this ECH index is. So that's actually the part that I want to emphasize. But if you had no idea what the heck I was talking about with this J-holomorphic curve stuff, I'll give you an opportunity to ask. So this ECH index y, I, here the ECH index I is given by, okay, so I take I of my curve C. It has three terms. It has a Chern class term. It has a relative self-intersection term. And it has a Conley-Zender term. So I don't want to go into too much detail about what precisely these are. So this C tau is a Chern class. This Q tau, this is a bit unusual. It's not what you see normally in this holomorphic curve theory. So this is a relative self-intersection. And this CZ upper I is a total Conley-Zender term. A total Conley-Zender term. So I'll say a few words about this in a moment, but I want to see if anyone has any questions about any of this stuff. I mean, there's a whole range of questions you could ask, ranging from what is a J-holomorphic curve to more technical questions about ECH. So are there any questions about any of this kind of thing, or things you can't see? So people are either happy or lost. I guess I'll just assume people are happy. Anyways, it's not so important that you know the details. Like I said, there's a lot of details, but it's good to get a feel. It's good to get a feel. So what do I mean by this Chern class term? Well, I have this contact structure, and I can pull back this contact structure to R cross Y. I just want to take the Chern class of that contact structure restricted to the curve, But this is some curve with boundary, topologically. So I need to take a relative Chern class. What do I mean by this self-intersection? I mean, this is some four-manifold. And I have a curve sitting in the four-manifold. So I can compute its self-intersection. But again, I have to be a little careful because there's a boundary here. So that's, again, why I need to pick some trivialization. That's what this tau is. And then these Conley-Zender terms, they measure information about the dynamics of these Rabe orbits. So this tau, yeah, exactly. That's a very important point. So this tau is a trivialization of my contact structure over all Rabe orbits. Right. Yeah, that's the interesting point here. And in fact, that was the next thing I was going to say. I mean, maybe I'll just put a little genus here to emphasize this. There's no a priori bound on the genus. The only thing I know is that the curve has ECH index 1. So if I want to learn something about the genus, I have to understand something about what it means to be ECH index 1. So the upshot well, I equals 1 curves can have genus. In fact, they can even have multiple components. But the key point, which we won't prove, is that this condition that I equals 1 forces the curve I equal to 1 implies that the curve is, well, mostly embedded and rigid mod translation. Okay? It's embedded before projecting. Yeah, we'll get to that in a moment. But that's already a good sign. So first of all, this is why it's called embedded contact homology. Second of all, you should think of this as a good sign. We wanted to find some embedded global surface of section, and at least this is giving us some embedded curves in R cross Y. They might not be embedded when I project to Y. It's a point. What is what? Oh, well, actually, these curves, they can have multiple components. What happens is that I always have an interesting component which is embedded, and then I can have some R invariant cylinders. So you should, the kind of picture that you should have in mind is that I could have an R invariant cylinder like this. And that might not be embedded. I could have a multiply covered cylinder here. But I always have a non-R invariant. I have exactly one component which is not R invariant, and that is indeed an embedded curve. Okay, so that's all that's meant in the mostly. Okay. So I got this thing. So now, the thing that makes ECH very powerful and that perhaps motivates some of these odd definitions is the following wonderful theorem due to Taubes, which says that this embedded contact homology is canonically isomorphic to the Seiberg-Witten floor cohomology of Y. Okay, so there's a grading here. I'll actually discuss the grading in a moment. Okay. Of my manifold Y. Now, the Seiberg-Witten floor cohomology depends on a choice of spin C structure. What happens is that there's a canonical spin C structure associated to my contact structure. And then my class in H1 just acts. There's a way for classes in H2 to act on spin C structures. anyways, that level of detail is not so important. The key thing is really this isomorphism linking contact and symplectic geometry to low-dimensional topology and gauge theory. Okay, so this HM upper hat is the Seiberg-Witten floor cohomology. So, of course, probably very few of you know very much about Seiberg-Witten floor cohomology. It's not so important. The important part is that it's defined using very different ideas, and it has some nice properties, which are not at all obvious on the contact and symplectic geometry side. So this Seiberg-Witten floor cohomology, it's an example of a gauge theory. It's generated by solutions to the three-dimensional Seiberg-Witten equations relative to a differential that counts solutions to the four-dimensional Seiberg-Witten equations. And there's a whole literature about this Seiberg-Witten floor cohomology. I mean, Kronheimer and Moravka wrote like a 700-page book, for example. So the power of this isomorphism is it allows us to take facts about Seiberg-Witten theory, which might be relatively easy to see on the gauge theory side, and translate that to facts about the contact geometry of Y and facts about holomorphic curves and the symplectization of Y. Okay, so that's this very powerful theorem which powers the whole thing. In particular, remember, we want to find some holomorphic curves, and we're going to find them this way. Okay. Okay. So, anyways, in the remaining time, we want to fill in some more of the details. Okay, so let's use some of this machinery to fill in details. So how does the proof go? Okay. Well, the first point is I actually want a lot of holomorphic curves. So one, I want lots of holomorphic curves. Okay. To get this, I want to use another structure on ECH called the U map. So there's a map, U. So there is a map U on ECH. It decreases the grading by 2. Okay? And it counts I equal to 2 curves in R cross Y. Well, so the I equals 1 curves, they're rigid mod R translation. These are not going to be rigid mod R translation. I want to count them. So I want to put them through a mark point. Marked point. Let me write it as 0, Z. It agrees with an analogous UMAP on HM hat. Okay, so all this machinery then implies, so this is by the whole Taub's isomorphism. Okay. So because it agrees with this map on HM hat, I can compute that I have a lot of holomorphic curves. So what I want is that there always exists what I call a U sequence. So there's always a sequence of classes sigma k on ECH where the sigma k's are non-zero classes in ECH where the sigma k's are non-zero classes in ECH, and U of sigma k is equal to the previous sigma k. So it's called a U sequence. So called a U sequence. So by using known properties of Seiberg-Witten together with Taubes' theorem, I get lots and lots of non-zero classes on ECH related by the U map. Remember, this U map counts I equals 2 curves. So this implies that I have lots of curves. There's lots of curves. I mean, I have an infinite sequence like this. So I have infinitely many curves. And I just have to show that one of them projects to a global surface of section. So I just have to show that one projects to a global surface of section. Okay. So, well, with my remaining time, what? Yeah. So, well, you'll see that that'll come up already in what I say. So with my remaining time, I want to tell you how do I have some control over whether this projects to a global surface of section. So I have some proposition. So, you know, when do I get a global surface of section here? So assume that C is counted by U. Assume, well, the following. So I want the genus of C to be equal to 0. I want C to have no ends at positive hyperbolic orbits. And I want C to have, C does not have 2 ends, at the same orbit. To, you know, positive or negative. Okay, so I have some assumptions. We won't really have time to say why they're relevant, but we can at least say the upshot. So then C projects to a global surface of section. Okay, so what's the point? Well, the point is, I have some things to check. If I want a global surface of section, well, I wanted a genus 0 global surface of section, but actually that comes up in the first place. I have some other things I have to check. It's not so important that you actually memorize all of them, but get a feel. You can't have ends at positive hyperbolic orbits. You can't have two positive or negative ends at the same orbit. You want to be counted by the UMAP. Okay, and then you project to a global surface of section. So the point is then, how do we find a curve? The upshot is we've now isolated what properties we want in our curve. And another extremely important point is that the moduli space of curves containing C is compact. Okay, so we've isolated the properties that we need. Now we have to check this. So now the idea is we sift through our infinitely many curves to find at least one satisfying this. So we show at least one curve satisfies. The U sequence satisfies this. Sequence satisfies all this. And to do this, we develop, we need machinery. For controlling topology of the curves. And unfortunately, it's too much detail to tell you about that machinery. But we have our paper. You can read it. You can ask me about it. Basically, what the machinery is it's a variant of this ECH index called the J index. And it gives you better control. So we have this J0 index, and then you need even more machinery to understand the J0 index. But at least this gives you the basic idea. So I think I'm going to stop here.